So students, as the name of the chapter is work, energy and power. So we started our chapter with the formula of constant work, that is F dot D. So work is a scalar quantity. It is dot product of force into the displacement. And that is equals to Fd cos theta. So this is where we started our chapter, and then we also written this formula as fx dx plus fy dy plus fz dz, means the work done by the force fx when the displacement is in their next direction, work done by the component of force Fy and then component of force Fz. Our second topic was work energy theorem. So according to work energy theorem, change in kinetic energy is equals to the work done by all forces. So this work done is by all the forces. Then next topic we did was work done by variable force. So work done by variable force can be written as, if it's in x direction, so from xi to xf, this is the displacement, and force is continuously changing. So force is a function of x. Here the force was constant, so this formula is for the constant force, and this formula is for the variable force. And then we did that this is the in circular motion. If we have a string, then this is the tension in the string which is providing the centripetal force, and this object is moving in the circle and a string is attached to it. We have studied that the work done by this tangent force. So what is the work done by this centripetal force? So work done equals to F dot D, and that's equals to centripetal force into the displacement into the cos of theta. So what is displacement here? So the displacement in this case, the direction of velocity, direction of displacement, both are along the tangent. So this angle is 90 degree. So the angle between the displacement, direction of motion, and centripetal force is 90 degree, and that is equals to 0. So work done by the tension force is equals to 0, because the angle between the tension force, which is the centripetal force, and this D is 0. So we studied this important point. Second thing is that still if you would like to write C, then what is the force, centripetal force here? So force is equals to m into A. So m into AC. And what is centripetal acceleration? That is equals to V square by R. So that's the formula for the centripetal force. Now after this we did the next topic, which is work energy theorem for the variable force. So this work energy theorem is for the variable force also, and it is for the constant force also. And we studied that students, graphs are very important, and see what is there on the x-axis and y-axis, that is again very important. So if this is the graph between force and displacement and position, this is the position, and this force can be constant force, this force can be variable also. So if this is xi and this is xf, then this area, force into displacement, this, or it can be if the, or this area, this is xi and this is xf. So this area is your work done. So if suppose xf is up to this point, then there will be a triangle and this area. So triangle of area plus triangle of rectangle, you can calculate, and for this we have variable force, so this formula we have for the work done. So that's the work done by the variable force. This is what we studied. And after that we studied very important concept of potential energy. We studied the concept of potential energy. So concept of potential energy is only in case of conservative forces. Only in case of conservative forces. And then we studied that this conservative force is nothing but derivative of this potential energy, and potential energy is a function of x. So we did this as general case. So what is the significance of this formula? So suppose if this is x position and this is your and on this y-axis you have the potential energy, then you will have a curve also. So this is the curve. Suppose as x is increasing, potential energy is increasing, so raising the ball, so x is increasing, so potential is increasing. So what is the force? Force is du by dx. What this differential is telling you? This is telling you the slope function. This is telling you the slope function. So this is the slope function. So f of x is slope function of u of x. Slope function of this curve u of x. So this is the slope function f of x. So the slope of this line, this curve, this graph is your f of x. So that is the meaning of this definition. So even this is how we define potential energy, by this formula. And further, now if you have a graph between f and x, same is this graph, right? Then this work done that I have written over here, this work done is equals to minus delta v, or you can now write it as minus vi. So v and u are two symbols in your book. You can always take u, so that's minus delta u by And you can further write it as W is equals to minus Ui to UF and du. So you'll get the same thing, that is negative of UF minus Ui. So this and this, so they are all concepts of conservative force. Okay. Work energy theorem is not a concept of conservative force. We have not studied conservative. We have started conservative force from this point. So work energy theorem is for all the forces, whether it is friction force, any force, whether it is conservative or non-conservative. So it is for all the forces. Okay, but the concept of potential energy is only for the conservative force. These formulas are only for the conservative force. Now we have studied one more concept of the conservative force, and the third concept was that total mechanical energy, that is K plus V, is equals to constant. Means there is no change in, change is zero. So that was another concept, and that is the concept is that mechanical energy is conserved. So student, this is conserved only in case if we have conservative force. Okay, and this work done by the conservative force, you can clearly see it depends on so the work done depends only on initial and final position and independent of path and independent of the path taken by the object. So these things are only for the conservative force. So non-conservative forces, I told you that the forces in which heat is dissipated, so we also call them dissipative forces also, drag forces also, and the example of that is friction force. And we studied the formula for the friction force. If this is the object moving in this direction, and so obviously there is no movement in the y direction because it is moving along the x direction. So here this force is mg and this is the normal reaction, so it can be r, we write it as r or n. So what is the friction force here? So the friction force is given by is equals to, so this is the kinetic friction if it is moving, mu into n. So this is the formula for the kinetic friction. And if I'm moving on the inclined plane, then what will be the friction? This angle theta. So this will be 90 minus theta. Normal reaction is always perpendicular to the surface, always. And now friction here is again nu into n. This is the coefficient of friction. Now what is n? N is equals to this, equal and opposite force, because there is no motion in this direction. So that is why these forces are equal. So now we have to find this component. So this is a component of mg. So this is your mg, and I told you that this angle will be theta. Why? Because this angle and this angle, they are corresponding angles. So this angle is 90 minus theta, and if this is 90 minus theta, then this will be, this whole angle is 90, so this 90 minus theta, this angle is theta. And what is this component? This is adjacent, right? Mg is hypotenuse. So this is mg cos theta. So adjacent is, you have studied this, sine cos. So what is cos? This theta. So the cos will be, this is hypotenuse, so this side is hypotenuse cos theta and this side is hypotenuse sine theta. So this is mg cos theta and this is mg sine theta. So I want to find friction. So friction is equal to nu into n. So this normal reaction is equals to mg cos theta, because there is no movement along this direction. Even there is movement along this direction, this is the applied force, I am taking it upwards. So students, I don't know what this force is, but this whole concept you are supposed to find it. So this will exactly be taken as mg cos theta. Okay, then only it will move upwards. So what does this mean? It means if these forces are equal, it means acceleration is zero. Whatever the velocity started here with, same velocity will be here also. So students, don't get confused. Applied force will be equal to this force. You are moving it up with no acceleration. Okay. Now this is equals to mu into mg cos theta. So this is what the friction force is in this case. So we have just revised whatever we have done till now. And another important concept is Newton's second law, which is all the forces acting on the particle is responsible for the acceleration, for its acceleration. So F net is equals to ma. So this is what? Acceleration is zero. It means F net is zero. It means this force is equals to this force. So that is why F applied is equals to mg sine theta. So this also we used. So this is F net, and F net I have already told you that the acceleration will be in the direction of greater force. So students, we are going to use all these concepts today. Okay, now let us start with example 6.7. So in 6.7, there is a circular motion, and the motion is only half of the circle. Okay, only half of the circle. So this is the lowest point that you have, and this is point A, and this is the highest point, which is point B. Now I have a bob of mass m, which is suspended by light string of length L. So this is the bob here, and this is the length of the string it is attached with, and so this length L of the string, and it is imparted a horizontal velocity v0 at the lowest point A. So this is the v0 velocity, which is tangential, right, in the circular motion. So this is the direction of motion, body is moving upward, and then it is a semicircular trajectory in the vertical plane. So this is vertical plane, right? This is vertical plane. So means the body is moving upwards. Okay. And the string becoming slack at this point, B. So string is slack means that it is slacked, means T is equals to 0 if it is slacked. There is no tension in the slick because it is slacked, you can see. And here we have the tension in the string. So where is the tension? So the downward force is mg, and this upward force, which is equal and opposite here. So that's the tension force. So tension force is providing the centripetal force. Now we have to obtain an expression for V naught. This is what we need to calculate. What is V naught? And then we have to find the speed at point. So this figure is given to us. This is point B. Bob will pass through this point and reach here. So this is point. So it means this is actually point C. If this is B, then this is point C. So A, B, C. Now, what is the velocity at this point? So this is the direction of the velocity at this point. This is VB. What is the velocity at this point? Tangential, VC, right? So we need to calculate VA, VB and VC. Okay, so this is what we need to do. Now, what are the forces acting here? Are they conservative or are they non-conservative? See, we have two forces you can clearly see. One is the tension force, another is a gravitational force. Gravitational force, of course, this force is gravitational force mg, and this is conservative force, you know it. Now, what about the work done by tension force? So the angle between displacement, direction of motion, and tension is, so work done by, we just did it yesterday, work done by tension force, this is tension, this is the direction of motion, displacement. So work done by tension force is always 0. So we did it, right? So the work will only be done by the gravitational force, or you can call it gravitational force or gravity in short. So work is only done by the conservative force. So that is why we can use the concepts of conservative force. So what the concept that we can use is mechanical energy is conserved. We can use this concept, right? So as the potential energy of Bob is associated with gravitational force only, therefore total mechanical energy E is conserved of this system. So E is conserved, right? Now, what is the potential energy here at A? So the lowest point. So we assume that, so this is assumption, assume that, so it's our choice where we are taking the potential energy as 0. So at A, potential energy is 0 at the lowest point. Now, mechanical energy, you know that it's kinetic energy plus potential energy, that is conserved, that is constant, that is E. So E at A is equals to E at B equals to E at C. So this is given to us. right? So we have to use this thing. So E of A is equals to E of B is equals to E of C. Now what is the E of A? So E of A is equals to E of B is equals to E of C. Mechanical energy at A is equal to mechanical energy at B, equal to mechanical energy is same at all these points on the path. Okay, so mechanical energy at A, which is K plus U, this can be written as half m v naught square, right? This is the kinetic energy at A, plus what is the potential energy at A? That is 0, equals to what is kinetic energy at B? Half m, simply the velocity at B, plus what is potential energy at B? So we know it depends on the vertical height, not on the path taken. Whether you are taking this bob on this path or on this path or this way, work done by the gravitational force is 0, because gravitational force is downwards, and this way if you are moving, angle is 90 degrees. So the work done by the gravitational force, if you move in horizontal direction, is 0, and then you are moving up. So now the work done by the gravitational force is of course there, and that is equals to mgh. So it is independent of the path you are taking, how you are reaching B. The potential energy will always be the work that you have done. So I have done the work. So the potential energy stored is the work done by the external agency. So the force that I was applying is like force applied. So downward force was mg and upward force was force applied. So what is the force applied? Force applied is equal to mg. I told you that acceleration is 0 in all these cases. So don't forget this thing. And then only this whole force applied will be multiplied this force with displacement upward action. So work is positive mgh, and that is what is your potential energy by the external force is your potential energy, work done by the external force. Now what is kinetic energy at this mechanical energy at C? This is half m vc square plus what is the potential energy here? So now the distance is, how much is this distance? So this distance is twice of L, right? This is R, this is 2R, so this is 2L. So what is the potential energy? mg into 2L, right? So mg into 2L. So students, I have just written the mechanical energies of the bob at A, at B, and at C. Now I need to find out V0, VB, and VC. So V0 is the velocity at A. Now, what other thing that I have? So this was the first thing that I have used, and the second thing that I always know is, so this is equation 1. Now I know that F net is equals to m into A. So net force, that is Newton's second law. So what is the net force at A? So this is, students, instead of h, so what is h here? This is L, so we can write it mg L in the form of L, because L is the length, right? Radius, length of the, so this is mgl here. Fine. Potential energy at B. So now F net is equals to MA. That is Newton's second law. So I told you that this net force, let us see what two forces are acting at A. So acting at A, we have two forces, T is equals to mg. So this is tension at A point. Now I was discussing that this was at rest. TA was equal to mg. But if this is moving, if it is moving, it means TA is, because the motion is in the direction, okay, I have reached here. So the direction is in the direction of TA or in the direction of mg? Of course, it is in the direction of TA, right? This much I have moved upward. So it means TA is greater. So greater minus smaller is equals to mass into acceleration. So acceleration is centripetal acceleration. Centripetal acceleration, I told you the formula. So centripetal acceleration is v square by r. So we did it here. Centripetal acceleration, that's equals to v square by r. Okay. So that is m v square by r. So which velocity? V naught. So we have this velocity here. So TA minus mg is equals to m v naught square by r. So what is r here? R is the radius, that is your length. So let us write L here. Now students, I want to ask, it's always better to write the answer in the form of variables that are given to you. So TA is not given in the question, that TA is there, tension at the string at the lowest point. So we are not supposed to use this TA. We need to eliminate this TA if we are using this equation, because we don't need it in our final answer. So it's very difficult to eliminate this TA because I need one more equation with TA to eliminate it. So I don't think that I'm going to need it. Okay. Now, I have one good thing here, that this TC is 0 because this is slack, so TC is 0. So let me use this. So this was at point A. Now what will be at C? So same thing, at point C, F net is equals to MA, and that is written as, so which force do you have now here greater at this point? So the ball will come down if it is allowed from here. So which force is greater, students? Is it so here we have actually mg, and tension is 0 at this point. So the only force we have here is net force is mg, because TC is 0. So the net force on this point, at all the points mg is there. Mg is there at all the points, gravitational force. So the net force we have is only one force, that is mg. And that's equals to MAC. So that is m. And what is the velocity at C? So v square by L. So this is at C. So this is equation number 2. Here I don't have tension force. So can I use this thing over here to find the velocity? This mg, m, so m cancels out. So we have vc square is equals to gl. So we have found vc. So vc is equals to under the root gl. Now what about va and vb? So put the value of vc over here, and we can find, then we can equate these two equations. We can find vb and put the value of vc here, and then equate these two equations, so these two expressions, and we can get V naught. Okay, so it's your choice which one you want to take first. So let us take this and this first. Okay, so half m V naught square is equals to half m. What is VC square equals to GL? So put VC square is equals to GL plus, so from first, and this is equation number, so this is the same equation, right? This is equation number 2. So from first using second, and that is 2 mgl, right? So what this equals to? So this will be equals to, so multiply both sides with 2. So what do we get? And m will be cancelled out, of course. M can be cancelled out, students, miss, from this equation. We can cancel out m. Okay. So m will be cancelled out. And what the V naught comes out to be. So multiply both sides with 2. What do we get? V naught square is equals to GL plus 4GL, right? Multiplying both sides with 2, right? So this 2 will cancel out, this 2 will cancel out, and here we will 4. So V naught is equals to, so this 4 plus 1, 5. V naught square is equal to 5GL, and V naught is equals to 5GL. So this is what VC was. So now students, now you can use these two equations, this one and this one. These two expressions, equate these two expressions. So what do you get? Half m VB plus GL equals to half, what is VC square? GL plus G into 2L, right? So you can multiply both sides of this equation by 2. What do we get? MVB square plus 2GL, right, is equals to, so this 2 will cancel out, only GL plus 4GL. So this is 5GL minus 2GL will be 3GL. We don't have M over here. M is cancelled out. So why have we written M? This M is not there, students. This M was already cancelled out. Okay. So now what do we get? VB square is equals to 5GL minus 2GL, right? And this gives me VB is equals to under the root 3GL. So students, very simple question. We have just written the concept of that mechanical energy is conserved, that is mechanical energy, kinetic energy plus potential energy. So at all the points A, B and C, and then we use Newton's second law. So this is not going to work at A, but okay, we have written the formula, but this is not needed actually. So in exams you can directly write for C, because at C tension, because there was slack in the string, so the tension at C is 0, so the only force at there was, so F net is equals to MAC, so only force was gravitational force, and that is mg, and that is equal to mv square. So we got VC from here, and put the VC and equate it with V naught, this expression. Now put the value of VC and equate it with VB. So such a simple concept, and we have done this example. So students, now there is one more part to this question. And that part is, what is the ratio of, that is the third part of this question, the ratio of kinetic energy at B divided by kinetic energy at C. So kinetic energy is half m VB square divided by half m VC square. So what is VB? 3GL, right? VB square will be 3GL. So half m into 3GL divided by half m. What is VC? So VC square is GL only. So everything will be cancelled out and only 3 by 1, that is 3:1. So see the concept here, students, that at B the kinetic energy is thrice of C. Okay, so kinetic energy at B was thrice of the kinetic energy at C. So here the body was moving at 3 times more speed than this. Okay, so this is not the example of uniform circular motion because the speed is changing. You have seen that the speed here is under the root GL. Here the speed was at point B, it was under the root 3GL, and here the speed was under the root 5GL. So it is, the speed is decreasing, right? So kinetic energy is also decreasing, and kinetic energy is converting into potential energy. So that's the concept here. So you find the ratio. So kinetic energy ratio is 5:3:1. Okay, and in the same ratio, potential energy is increasing. Okay, so that's in the case of conservative force, because tension force was 0. So that is why only force acting here was gravitational force, and that is a conservative force. Now let us study one more conservative force that is very important. So one more conservative force is spring force. The potential energy of a spring. So potential energy of a spring. Students, I have a spring over here. So this is figure 6.7 in your NCERT books. And this spring is connected with this body. So this is my mean position. So there is no displacement. So x equals to 0. So x is equals to 0. There is no spring force. Now I have stretched the spring. You have seen it in your real life also. If you have stretched it, now this displacement is x. So this is the positive direction, so this is positive x. But tell me, students, this spring is pulling this body in which direction? The spring wants to go back to this position where it was at rest. So obviously force by the string is acting in this direction. Displacement was in this direction and string force is in this direction. Yes? Now let us see the case in which this spring was compressed. So the spring was compressed. So now I have moved here negative x. The displacement is negative x. Now tell me the direction of force here. Where this spring wants to push this back? Yes. So this direction of spring force. So here this displacement was positive, but the spring force in this direction was acting in this direction, that is the negative direction. So this direction is xy, so this is the positive direction. and this direction is negative x. So this direction was, so the Fs was negative here, right? And here in this direction, so x was negative whereas Fs was positive. Means spring force act opposite to the direction of the displacement, right? And that is what the Hooke's law is. So what the Hooke's law says? So we are assuming, what is the assumption here? Assumptions are very important, students. Massless spring. So what is this? So spring force is proportional to the displacement. Okay, more you stretch it, more will be the spring force. So spring force is not a constant force. It depends on the displacement. If the displacement only here, little spring force, more stretching, more spring force. Yes, and you will come to a point that you can't stretch. So only simple springs you have seen, but we can have the springs of all kinds, like shockers in your cars. They also have springs. Okay. So students, this is the force is directly proportional to the displacement, and it is negative. Both are in opposite direction, and the constant of proportionality, spring constant, that is minus k. So k is the spring constant. This is spring constant. This is spring force, and x is the displacement from the mean position, from this origin, when there is no force acting on it. So this law, this simple equation is known as Hooke's law. So very important, students. Hooke's law for the spring force. Now, what are the units of spring constant? So how do we find the units of spring constant? So k is equals to Fs upon x, right? So the units of force is Newton and meter. So units of k are, SI units of spring constant are Newton per meter. So SI units. So now students, dimension formula is also important. You can find it out. Important thing is that if k is large, if for large k, we call the spring as stiff spring, and if small k, small spring constant, we call it soft spring. The spring is soft if k is lesser. So k is lesser, so spring force will be lesser, right? So in spring force is lesser, and if k is more, spring force will be more, right? Okay. Now spring force is also conservative force, and so you can see that we have pulled the spring, this block outward, we have pulled the block outward, and if the extension, let this extension be the maximum extension, so x can be this, x is variable, can be this, can be this, but this maximum point, this displacement is xm. Okay. Now, what is the work done by the spring force? So work done by spring force. So work done by spring force means spring force into displacement. Can we use this formula here? No. Why? Because spring force is variable force. So we need to use the formula of the work done by the spring force as work done by the variable force. So that the formula is Ws is equals to Fs dot, so ds, right? And what this x varies from? X varies from 0 to xm. Okay, students, now put the value of Fs, that is equals to minus kx. So that's minus kx, so minus you can write outside also. So kx dx 0 to xm. Now you can see here that as the force and displacement are in opposite directions, so we have sign negative here. So I have not written negative here because already with Fs, force and displacement are in opposite directions, so I have taken this impact over here in Fs. So that is why I have written Fs into dx. Now that's equals to, so minus k, and what's x? So we know the formula, x raised to the power n into dx is equals to x raised to the power n plus 1 divided by n plus 1, right? So x dx will be, so here x n is equal to 1. So if n is equals to 1, then this 1 plus 1 is 2 divided by 2. And these are your limits 0 to xm. So put the final limit xm square at the place of x, put the final limits divided by 2 minus the initial limits. So the initial is 0. So 0 upon anything is 0. So there is no need to write it. It is 0. So students, that is the work done, right, by this spring force. Okay. So you have these two important things, spring force and the work done by the spring force. Okay. And work done by the applied force will be positive in this case, right? So work done by the applied force will be kxm square by 2. So applied force will be exactly equal to Fs. This is, I am regularly telling you, because here I am taking the acceleration to be 0. I am taking it at very small pace, very small speed. Students, this is the concept of potential energy of conservative force. You have to move it with very, very slow speed. Okay, acceleration is 0, and that is why we are taking applied force is equals to spring force, and in earlier cases also. So remember this thing. So the work done by the spring force is minus k xm square divided by 2, right? So because here the spring force and displacements are in opposite direction, so these are the two important formula. Formula number 1 Fs and formula number 2. Now students, we also know that for conservative force, W equals to, work done by the conservative force is equals to negative of change in potential energy Yes. So this is Ws. So what is change in potential energy here? Change in potential energy here will be equals to, so this you can write it as this equals to minus W and put the value of Ws here. So minus minus will be positive and we get K xm square by 2. So this is the change in potential energy. And that is equal to, so what is change potential? Final minus initial? Oh, sorry, not kinetic, we are talking about potential. So final minus initial, this is what change means. And initial was 0. So at this position we have taken, so this u was 0 over here at this position. Okay, so ui was 0. So if this is 0, then this uf is the potential energy stored here at this point. So potential is stored here is given by K xm square by 2. Okay. Students, if you want to verify it, see, we have, remember, we started our lecture with this formula, Fx equals to du by dx minus du by dx. That's another way of writing it. Work done is equals to minus delta V. That's another way of writing it. So work done is equals to means you can do it. Work done is equals to minus delta U. So work done is equals to F delta X is equals to minus delta U, and F is equals to minus delta U by dx, and taking the limit delta X tends to 0, then this Fx is equals to minus du by dx, right? Now let us see for gravitational force and spring force. Put this value of u here. So Fx is equals to minus d. So potential energy stored at height is mgh, and this also will be written dh. So the force comes out to be minus g. So minus g is constant, dh by dh is 1. So that's the force. So upward direction I am taking positive, this downward direction is negative. So minus, so this is the gravitational force. Now what is the spring force? So same, put the value of u here. U is this, so that's minus d by dx of kxm square by 2, and that's equals to, so this is gravitational force, what the spring force will be equals to. So 2 will come forward in differentiation. What is the formula of differentiation? D by dx of x raised to power n is equals to n x raised to power n minus 1. So here x square, so d by dx of x square will be equals to 2 raised to the power 2 into x, 2x. So minus, k is constant, so xm is 2xm divided by 2. So 2 will cancel out, and that is equals to minus kxm. So this is what Hooke's law is. Fs is equals to minus kx. Fs is equals to minus kx. So students, I've just shown this thing to you, okay? And this is, I told you, this is the slope. Fx is the slope of the graph between potential energy and the position, okay? Now another important thing is, let's see how the energy transformation taking place. So this is my position, And this graph, I have plotted the energy over here. Energy, kinetic energy, potential energy, all the energy is over here. Okay? Now, let us write kinetic energy. So students, this is the graph I am drawing for the energies, how the energies are varying along with the position x. You know what the position x is from the mean position, this displacement. So this displacement was xm and minus xm in both the directions, right? Remember, when the spring was stretched, it was xm, and when the spring was contract, it was minus xm, right? And this is 0, equilibrium position. Now, let us draw the graphs of 1, 2 and 3. Obviously, first thing is that the total mechanical energy, this is the total mechanical energy, which is E. So E is equals to kinetic energy plus potential energy. That will be the same. So this is the graph of that straight line, because this energy is constant. You are at minus xm, same energy. You are at this point, same energy. You are at this point, same energy. You are at this point, same energy. You are at this point. So energy at all the points is same. Now, what about the graph of potential energy? So at 0, the potential energy was 0. So let us see what we are doing. This is your spring, and I have stretched it, okay? I have stretched it. So this was your mean position, and I have stretched it to plus xm. Now it will go back, right, due to spring force. Here the spring force is 0, because at the mean position the spring force is 0, but still due to inertia it will move further. Due to inertia it is moving further, because the body in motion will remain in motion. But now as it started moving from this place to this place, spring force acted back in this direction, and here the body stops at minus xm. So the body will again come back, and Fs is 0 here, but due to the inertia it will move again to this position. So it will keep on moving. It started from here, this spring will keep on moving like this. This simple harmonic motion, we will study it in book 2, but this is how it will keep on moving this way and this way. We have studied this bob over here, it is hanging over here, so it will keep on moving this way and this way. Same is the case here. Spring will move this way and this way. So how the energy transformation take place? Then it will move in this way, right? So let us find what will be the maximum speed, and at maximum speed we will have maximum kinetic energy. So obviously at this point you will have the maximum speed, even for the bob also you will have maximum speed over here. So kinetic energy is maximum at this point. So if you draw so kinetic energy is maximum and potential energy is 0, right? So kinetic energy is maximum, and here the velocity is 0, here the velocity is 0. So this will be the graph of, this parabola will be the graph of kinetic energy. And the graph of potential energy will be, so this exactly when the kinetic energy is 0, obviously potential energy is maximum. Here the potential energy is 0, and here the potential energy is and again maximum. So this will be the graph of potential energy. This is the graph of potential energy, and this was the graph of this color, graph of kinetic energy. So students, but you can clearly see that when the object is moving from this point to this point, so from even here to here, potential energy is increasing, kinetic energy is decreasing. At this point, we have only potential energy, kinetic energy is zero, body is stopped and coming back. And when it is coming back, then potential energy is decreasing and kinetic energy is increasing, potential energy is decreasing, potential energy is zero. At this point, in the mean position, there is no potential energy. But as it will move further in this direction, potential energy will again start increasing and kinetic energy will start decreasing. So that's what this graph is. Now, little bit more patience I need from your side. So we have defined the potential energy of the spring is zero in the equilibrium position. So here U was is equals to zero and this is the equilibrium position. And we know that Ux is equals to k x square by 2, right? Now, if this block has mass m and it is extended to xm, then the total mechanical energy at any point will lies between what the potential energy will be given by. So the mechanical energy is equals to kinetic energy plus potential energy. This energy will be given by this formula. The total energy is see students, what is the total energy here? What is the total energy? This we have only potential energy here, right? And E is equal to U at this point. At this point, E is equals to U. At this point, E is equals to K. Again at this point, E is equals to U. Because K is 0 here, U is 0 here, and K is again 0 here. So mechanical energy is equal to potential energy. What is the potential energy here? Potential energy is K. What is X here? Xm square by 2. So this X is any point. Okay, so this is the general formula for potential energy. But what is the potential energy here at the extreme? That is K. So this is the total. I can write it as mechanical energy, right? Because here the mechanical energy is equals to the potential energy because kinetic energy is 0. So I can write it as kxm square divided by 2. So this is your. So now I am writing it at any position x. So at any position x, students, so suppose this is the position x. I'm talking about this position. So obviously E is constant. E is this thing is constant. This is not going to change. This K and U is going to change along with x. So what is your K? K is equals to half mv square, right? Plus what is your potential energy? Potential energy at any point x is given by half k x square by. So either write 2 here or here, that's the same thing. So half kx square. So now the speed and kinetic energy will be maximum here, yes. So at O I have kxm square by 2 is equals to, so at O E is equals to your kinetic energy, right? Because U is 0 here, and that is equals to half m. What is V? V, so we write here, let us write here this velocity is V maximum, okay? V maximum. So that's the maximum speed. Now let us find this maximum speed. So 2 will cancel out. And maximum speed at equilibrium position O. So equilibrium means what? potential energy is zero, not kinetic energy. So when it is moving, right? So what is the maximum velocity here? So that is given by, so this Vm will come this side, and so the Vm square is equals to, so at O, Vm will be maximum, and that is given by under the root K by M into Xm, right? So Xm is square root, so square rooting both sides, K by M into Xm. So students, the kinetic energy is maximum at, and that is why velocity is maximum. So this is the velocity, maximum velocity we have calculated. So thank you so much. Today we'll do examples and some of your problems. Thank you so much for being with me today.